All right, we are back. We are on episode number 50, and we're going to keep discussing the dental transducer that I showed you in the last episode. Today, we're going to be doing some impedance measurements on seeing how that holding mechanism of putting an O-ring at the front and pushing back against the transducer on the soft pad, um, how that actually ends up affecting the performance. Now, there's two methods that we use to determine how holding affects performance. The first, and one of them, is frequency. That how after you have administered holding your or clamping your transducer into its holder or shell, whatever you want to call it, how that affects the frequency, because that's the mechanical stiffness and mass of that contact. Now, if the contact is not rigid, you're likely not going to be really affecting frequency very much, although you will decrease frequency if you damp. But when you do damp, your quality factor is your major mechanism of understanding how um, how you've really affected that damping. So let me go ahead and flip to our camera here, and so I can kind of show you this transducer up close. I'll flip it. So let's just change this here. Okay. All right, and we're good to go. So we have our transducer here, um, and now I will actually also throw up the impedance plot that we're going to be measuring. So I have an impedance analyzer made from an oscilloscope, function generator, and a ground side resistor. I'm just going to go ahead and hook up the terminals here. And as you know, for low voltage, it doesn't matter positive or negative, however you hook things up. Anyways, it's AC, unless you're using a bias. So there you just have your transducer sitting on a kind of piece of napkin. I already know the frequencies between, I think, 40 kilohertz and 50 kilohertz, and I'm going to be using a frequency step of, and I want to make sure you guys can see this. Um, I want to using a frequency step of 100. We have a ground side resistor of 100 ohms, and we have a couple of points here that we want to go. File name empty. Oops. Anyway. Okay, so that's our transducer. So we don't see very many points around the resonance frequency from which we're going to be calculating. Let's just run a Q measurement right now. That gets us to 220. So I want you to notice what happens when I increase the number of points. This is a really big issue, not having sufficient points in your analysis. So we're going to be running now 10, and I do want to get a little bit closer so it doesn't take forever. So let's go to from 43 to 46 kilohertz. And this is the bare transducer, as you see in the picture. And let's run that again. And I'm going to be kind of putting the transducers properties in as we kind of go here. I just want to correct one of these impedance settings. This is change it here and then change it back because it's not getting the right values. Okay. So we went from 220. Now we're at 258. So it doesn't make a good difference on your frequency versus your the number of points versus the Q measurement. So we have a frequency of 43. We have a frequency of, which is shown right here for the resonant frequency, 43.9 kilohertz, and we have a Q of 258, and we have an impedance shown right here at 318 ohms. And that's the transducer. And I'm just actually typing all that in here. I'm saving you the grief of watching me. So there you go. But I'll get back to that. Now, I want to show you with this holder that we have here. And I'm just going to do you guys a favor and open this up here so you can see that a little bit better. I'm going to stick this O-ring on here. That's where it went. And I'm going going to support it at the back, like so. And if you see this holder here, it has it's not, the top part is not, um it's not circular, so it does go onto these flats of this transducer that would help it to keep from twisting. So that plastic, that plastic interface to the flats would keep it from twisting when you're actually, oops, I dropped that, when you are putting on a tool. So when you're putting on a tool, it'll keep that from twisting, as long as that's also secure in the other holder. So let's do this. You only live once, so let's make this happen. So I'm going to hold it like that. And let me just reduce that size so you kind of know what I'm doing. So I'm going to make sure I don't. So I'm holding it there just like it would be held inside of the transducer, or inside of the holder there. So let it do its thing. So the black plastic part on the front is pushing back against the O-ring, which is pushing back against the base of the horn of the transducer, and then the back is supported by a pad and a plastic piece. All right, so let's now push that button. So we got to a Q factor of 199. So I'm going to log that data. Transducer holder. The Q factor was not 199. The impedance was 425 ohms, and the frequency is 43.9. It actually increased 40 hertz, but I'm not going to count that. So let's just take a look at what happened here. When we held the transducer, we decreased it by 50, quality factor of 50, and the impedance went up 100. This is significant, but it's not a huge red alert like this holder is garbage or it's not working. So it actually didn't damp it out too much, but there is something else to the story. I won't be able to show it here just yet, but let's just, for demonstration's sake, continue with this, and let me squeeze it really tightly, just really tight, just to show what could potentially kind of happen there. I'll squeeze it really tight. Obviously, if it's mechanically clamped, it wouldn't be an issue there. Careful not to touch the tip of the transducer, but just clamp in between these 2 points. All right, and I'll press this button here. So I got to 169. So I'm gonna type in all of these as we go. I have another screen here. We're gonna call this the transducer with stiff, with high pressure. So we'll distinguish that. The frequency now is 43.998. So it seems to be increasing actually as I clamp down. Actually, I'd say 44.0. The quality factor is 169, and the impedance is 504. So here we go. And I'm just going to throw that here. I also want to show you a trick too in one moment. But as we start increase the amount of damping, where the impedance is going up, the product of these two numbers probably is going to remain the same. So this times this. Okay, come on. Yeah, the product of these two numbers didn't change very much. Even though this number decreased significantly, this number almost increased, not by double, by 1.5. But basically, as the quality factor increases, the impedance decreases. So, but that is only true. This ratio is only common if your coupling factor is similar. So that's the resonance and anti-resonance, which shows that the general structure of the resonating system is the same. It's just that you introduce damping. So purely adding damping is going to increase impedance. Conductance is a better term for this, the real impedance, but here we're just kind of simplifying and using impedance. So this is just the Q times Z, and that's kind of constant here. It's very constant actually in comparison. It's only moving up by like 2% versus just as tens of 20 to 30 or 40% changes there. So it's a pretty good ratio. And that's dependent on the frequency being constant. So this is what happened when you damped the transducer by holding it. Um, so other things I want to mention here, although this doesn't seem like a lot of damping, like going from 258 to 199, it actually isn't. But the problem is that when you get to higher power levels, the oscillation of the oscillation of your device itself. Let me just blow that up for you guys. The oscillation of your device itself is going to start rubbing against and really causing even more losses due to higher power and higher oscillation levels. That significantly increases heat and damping in those areas. So you would be wise to test this under both multiple conditions, both high power and low. But we do see that even in low power, we are reducing Q. So that's a concern there. So this Q factor being 258 might be mostly due to the crystals. Based on crystal choice, you are limited in your Q factor, because metallic components usually do have a higher Q, but you get larger bandwidth of operation, so you're not as sensitive to whether your transducer is actually, whether when you have a tool, when you're impacting the tooth, that you're gonna be able to lock on frequency better. I think I will show you with the scalar tool, not today, but we'll go over that in the future here. So let me just get myself back on the screen. All right, here's me. So you've been watching episode number 50. In this episode, we spoke about a dental transducer being held by its O-ring and the back side. I would probably have concerns with this if this was a very high power device, but since it's a low power device, you can get away with a lot more loose way of holding, a non-optimized way of holding the transducer. But it got the job done, and I think it's it's a lesson to learn about different ways of holding a transducer. The quality factor for this transducer was low. Was at 258, and I mentioned frequency, quality factor, impedance. Those were a couple of important parameters. I did show that the quality factor and the impedance, the product is actually constant, because as the quality factor increases, the impedance decreases. Actually the opposite. As the quality factor decreases with more damping, you have the impedance increasing, which basically means there's less current, less motion. That's constant because they're inversely related. The fact is that damping that I was putting on wasn't mechanical coupling or mechanical stiffness coupling and mechanical mass coupling. It was just purely very pure damping, which could also be seen by the small change in frequency. Basically, you start at 43.820 or 890 kilohertz. This 980 hertz, and it just went up 40 hertz approximately every time you increase that level of damping. So I hope you enjoyed this video. Check out the description for links to my consulting services. Subscribe to this shock show. There's a link to do that as well in the description. You'll get the presentation notes in your email, as well as a link to watch the videos as they come out. And you can also, of course, subscribe through YouTube. All right, I'll see you next time in episode number 51. We're going to continue analyzing this ultrasonic dental transducer. It's been pretty fun.